Hello, my name is Andreas Booty, and today is August 22nd, 2020, and this is the Case Connection 2 video assignment. And what I'm going to do today is to discuss Case 1 and Case 4. So in Case 1, pyruvate kinase is the topic that's going to be talked about, along with pyruvate kinase M2, that's more uh, expressed in cancer cells than pyruvate kinase M1 isoform. So what is pyruvate kinase? Pyruvate kinase is the enzyme that catalyzes the irreversible reaction of converting phosphoenolpyruvate to pyruvate along the production of with the production of ATP from ADP in that last step of glycolysis. Now there are three regulatory enzymes in the glycolytic pathway. So one is the glucokinase or hexokinase, two is the phosphofructokinase 1 or PFK1, and then three is pyruvate kinase. Now we're going to talk about pyruvate kinase. Pyruvate kinase, the regulation of pyruvate kinase is activated allosterically by a number of molecules, and these include fructose 1,6-bisphosphate, serine, and succinyl aminoazole carboxamide ribose 5-phosphate or SYCAR. Now, fructose 1,6-bisphosphate is a glycolytic intermediate. It is converted from fructose 6-phosphate and it is catalyzed by PFK1 along with ATP from ATP to ADP. And SYCAR is an allosteric activator exclusively for pyruvate kinase M2 isoform. So it allosterically activates just pyruvate kinase M2. Moreover, pyruvate kinase is also allosterically activated by small molecules and metabolites, such as amino acid. However, high concentration of these molecules and metabolites are required to induce any positive effects at all. Pyruvate kinase is also activated by post-translational modification of the enzyme, such as phosphorylation, oxidation, and acetylation. Now, on the other hand, pyruvate kinase is allosterically inhibited by a number of molecules, including ATP, glucagon, phenylalanine, and alanine. So glycolysis is decreased through feedback inhibition by ATP, and ATP binds allosterically to pyruvate kinase to decrease its activity. Now, alanine allosterically inhibits pyruvate kinase of the M2 isoform only. So not PKL in the liver or PKM1. Now, the thyroid hormone triiodothyronine, or T3, also allosterically inhibits pyruvate kinase. Pyruvate kinase isoform M2 is found mostly in cancer cells instead of the isoform M1. And the reason for this is probably because ATP production from pyruvate is not the only pathway required for cell proliferation. In order for a cell to multiply, either normal cell or cancer cells, so the energy needs to be abundant, hence the ATP. But also DNA needs to be replicated, and the cell membrane also needs to be large enough for a cell to be divided into two. So therefore, the phospholipids in the cell needs to be abundant. All the substrates required to satisfy these conditions are included in the intermediate molecules in glycolysis. The decreased activity of pyruvate kinase isoform M2 renders it possible for the glycolytic intermediates to be accumulated and as a result to be used for other pathways. For example, glucose 6-phosphate is a required substrate in pentose phosphate pathway. Now, pentose phosphate pathway is utilized to provide the building blocks for nucleotides and also the reducing equivalents required to produce them. So ribose 5-phosphate or phosphoribosylpyrophosphate pyrophosphate are the building blocks to build nucleotides, DNA, RNA, along with NADPH as the reducing equivalents. So therefore, ultimately, there are more substrates needed to multiply the DNA, compared to the pyruvate kinase M1 isoform. Pyruvate kinase, anyway. Other glycolytic intermediates are also used in other pathways. For example, 3-phosphoglycerate is used to synthesize serine and in turn glycine. The hydroxyacetone phosphate is a substrate for the synthesis of glycerol ethyl phospholipids, which are important for cell membrane. Now, case 4. Now, this is a case where the baby has a few symptoms, including jittery spells, hypoglycemia, and hepatomegaly, and with the infusion of epinephrine, there's no the glucose level is still low in the fasting state. The most likely diagnosis for the patient is glycogen storage disease. The jittery spells are caused by the decreased levels of glucose in the blood, so hypoglycemia. Since the glucose levels are normal immediately after feeding, but abnormally low during fasting state, this shows that one of the mechanisms to maintain the normal levels of glucose is defective. Glycogenolysis is the most likely pathway to be the one affected. This is supported by the hepatomegaly. So the liver functions as glycogen storage. So if glycogen keeps being accumulated without being used, it would expand the size of the liver. However, during fasting state, glycogen is not available to be used to maintain normal glucose level in the blood. Even after the infusion of epinephrine, which stimulates glycogenolysis, it did not normalize blood glucose level. So all the symptoms combined points to glycogen storage disease, or COC. Now, choice A is wrong because there's no indication that fructose metabolism is affected. The mother states that the baby has been fed only with breast milk when she was born, since she was born, should I say. The main sugar in milk is lactose, which is metabolized into galactose and glucose in the liver. Thus, the baby was not given any fructose or sucrose ever since she was born to life. So in hereditary fructose intolerance, the patient experiences hypoglycemia or low blood sugar because, one, there's accumulation of fructose 1-phosphate, and this is because the enzyme aldolase is deficient, and 2, fructose 1,6-bisphosphate. These two intermediates, they inhibit glycogen phosphorase allosterically, and thus as a result, glycogen is being stored but cannot be broken down into glucose through glycogenolysis. Now, choice B is wrong because level of glucose was found to be normal immediately after feeding. Now, choice B is galactosemia. Galactosemia is a group of inherited disorders that affect galactose metabolism. A variety of enzymes in the galactose metabolism pathway could be affected, but the most common deficiency is the galactose 1-phosphate uridyl-transferase deficiency. In this case, when galactose is consumed, galactose is phosphorylated to galactose 1-phosphate. Galactose 1-phosphate uridyl-transferase catalyzes the formation of glucose 1-phosphate from NUDP-GAL from galactose 1-phosphate and UDP-GLC. However, in galactosemia, this reaction is halted. This means that glycogen synthesis should be impeded by the patient if the patient is in galactose-only diet. However, in this case, glycogen synthesis occurs and accumulates in the liver with galactose-only diet. It means that galactose metabolism works properly, and therefore the problem is not galactosemia. My choice D is wrong. Glucose 6-phosphate dehydrogenase is the enzyme that catalyzes the reaction of glucose 6-phosphate with NADP plus to 6-phosphogluconate in pentose phosphate pathway. This pathway is important because it produces NADPH and building blocks to build DNA and RNA. NADPH is important a reducing agent in red blood cells as it functions to act to reduce glutathione, which in turn reduces H2O2 to H2O. And this is important because H2O2 causes oxidative stress in red blood cells, decreasing its lifespan. When glucose 6-phosphate dehydrogenase is deficient, NADPH production is decreased or non-existent. And as a result, the red blood cells will not live for long, and the patient experiences hemolytic anemia. In the case of the baby, there is no indication of an hemolytic anemia, and therefore glucose 6-phosphate dehydrogenase deficiency is not the diagnosis. And again, this case, the answer to this case is most likely to be choice C, glycogen storage disease. Thank you.